This is a video reviewing Unit 2 in Calculus 2.1 through 2.5 in preparation for the test. So the first thing we did in this unit was talk about lines. And we talked about we reviewed slope, which is a rate of change. We reviewed the various different forms of lines and point slope, slope intercept, standard form, and then we talked about how parallel lines have the same slope, perpendicular lines have negative reciprocals. So it was a view of lines because in the second section, we talked about tangent lines. And tangent lines are important because in order to find the rate of change of a curve, we need to find the slope of a curve, but a slope requires 2 points. And so how are you going to find the slope of a curve at a particular point when you don't have a second point? And that's when we developed the idea of the derivative, which is the slope of the tangent line at a particular point. And the way we found how you find a slope normally is change in y over change in x. And we did that with using, so if we have like 2 points here, let's just draw a function. So say I'm interested in this particular point here. So I'm interested in the rate of change of this curve. We'll call this curve f of x. And I'm interested in, again, the slope at that particular point P. And so if we call this x, we've got this point x comma y. And then, but as we talked about, to find a slope normally, we would need 2 points. Well, we said, okay, let's take a second point here. And so if we're talking about finding the line through 2 points, or the slope through 2 points, we can do that. It's change in y over change in x. And we're going to call this x point x plus h, where the distance between these 2 points is h. So if I think about, this point, we'll call it q. We've got x plus h, comma, f of x plus h for its coordinates. So if I think of finding the slope of the line connecting P and Q, again, change in y over change in x, it would be f of x plus h minus, we can call this y of P, we can call this just f of x, minus f of x over the change in x values, x plus h minus x. Or in other words, if we simplified the denominator, the x's cancel and I get h. So this should start looking familiar. This is actually the difference quotient. But to find the actual derivative, which is the slope of this tangent line, that would be when these 2 points get as close as possible together. In other words, the distance between P and Q is tending towards 0, because the closer this Q gets to P, the more closely I'm going to approximate that tangent line and hence be able to find the slope of that tangent line. So that's why we said the derivative, which we can write as f prime of x, which is the slope of the tangent line, is equal to the limit as h goes to 0. So as the distance between those 2 points gets smaller and smaller of this difference quotient. And that's called the limit definition of the derivative. And so we did some practice with that limit definition of the derivative. And we could find that derivative using this definition. We could find it in general, or we could find it at a particular point, in which case we plug in that x value of that point. And then we could also find the equation of the tangent line. So that is what we did in the second unit, which was a lot. All right, meaning not the second unit, the second section of the unit. All right, let's move on and talk about, so then we did that limit definition of the derivative, but then we talked about, what are some shortcuts to finding the derivative? And we talked about something called the power rule. All right, so let's talk about that. So this was the third thing. So we've got this power rule. And that said that if I have a function that is some variable to a power, so x to the n, the derivative, or f prime of x, is n x to the, sorry, that n x shouldn't be up there, n x to the n minus 1. In other words, that exponent comes down in front, and then the original exponent of x gets subtracted by 1. So let's do an example here. So if I had a function equal 3x squared, the derivative is 3 times 2 and x to the 2 minus 1, or in other words, 6x. That would be the derivative. And if I want the derivative at x equals 3, I just plug 3 in for that variable of x. So that was the power rule. Then we also said if we have the equation of a line, so say f of x equals mx plus b, what's the derivative there? Well, the derivative is, remember, the slope of the tangent line. So if it's a line itself, the derivative is just m. And then we also, so this, the power rule we did the derivative of a line is just the slope of that line. And the third thing we said is the derivative of a constant, we'll just call it b. That derivative, no matter what the constant is, the derivative is always 0. So we did some practice with those. And then again, a practice finding a derivative at a specific point and finding the equation of the tangent line. And then we moved on to limits. So for limits, I think I'm on Roman numeral 4 here. So for limits, a limit means as x approaches a specific value, does the y value of the function approach something? So limits would not exist. It has to go towards a specific number if a limit exists, and it has to go to one number. It can't be going to two different numbers. So for example, so if we had, say, have something like this, and we'll say 1, negative 1. So if I said, what's the limit, and we'll call this function, this graph, f of x, the limit as x goes to 1 of this function, you would say does not exist, because the limit is different depending on which part of the graph you're coming from. And let's talk about this. You can often break down limits to whether you're coming from the right or left of that particular x value. So for example, for this problem, I could ask limit as x goes to 1 from the left, use that little negative sign. So if I go to my graph, if I'm on my graph going towards 1, so I'm here going towards 1 from the left. So I went to 1 and I looked at the left where the graph was. So in this case, the limit as x goes to 1 from the left is going to be 1. Whereas the limit as x goes to 1 from the right, where I use that little plus symbol, so again, I go to the right of 1. This is x being 1, that is. And if I'm going towards 1, the limit is getting closer and closer, or the y value is getting closer and closer to negative 1. So one important thing to note is that to be a limit, it actually doesn't have to be defined at that particular place. In fact, here, it couldn't be defined at both 1 and negative 1, the function, because then that wouldn't be a function. So that's why, so it just has to be approaching that y value to be a limit. So again, I could say that the limit from the left is 1 and the limit from the right is negative 1. But if I just asked what the limit as f of x, the limit of f of x as x goes to 1, you'd have to say does not exist, because it's different from the left and the right. So let's do a little bit more about limits. So that's if you have a graph. Actually, let's do a couple more with a graph, and then we'll talk about if we don't have a graph, but instead have a function, how to find limits. So let's see, what about if I had so what if I said here, what's the limit as x goes to 1 of the function? I'll say this is f of x. So if I'm looking at my function and I'm going towards 1, it looks like the y values are approaching. If I'm going from the left and the right towards 1 and I'm on the graph, the y values are approaching 2. Sometimes this confuses people because it's actually not defined at 1. There's no point at 1, 2. In fact, there's a point at 1, 1. Why isn't 1, 1 the limit? Because it's all about when you're on the graph, what is that graph approaching as x goes towards 1? It doesn't have to be exactly where that y value of 1 is. So in this case, the limit would be 2, not 1. Because you're looking again what's happening while you're on the graph as it's approaching x equals 1. What about instead if I had, let's do 1, 2, just something simple like, what if I said the limit as x goes to 2 of the function? Well, from both, if I'm on the graph going towards 2, from the left I'm going here, and from the right I'm going here, so I am going to the same place, and it actually is defined there too, which doesn't have to be, but it is. So it looks like the y value would be 2. And what about the limit as x goes towards 0 of the function? Well, as I'm going towards 0, here's x equals 0. From the left and from the right, it's going towards 0. So that just gives you a bit of an idea with a graph. Well, let's talk about the strategies if you actually have, I don't just give you a graph and say f of x, but I actually give you what f of x is in terms of x. What are the strategies there? Okay, so the first thing, so find the limit given a function. The first thing you do is you see if you can plug in. So for example, what if I said the limit as x goes to 1 of 3x squared minus 5? Again, we don't have a graph, we just have the function itself. Well, first thing you see is it defined there? Can I plug in 1? And when I plug in 1, I can here. I get 3 minus 5 or negative 2. So that's going to be the limit. So that's great. If you can plug in, woohoo, got it. If you can't plug in, see if you can reduce or factor and then plug in. So for example, let me show you that type of situation. What if I said the limit as x goes to 2 of, whoops, I don't want to write f of x, of x squared let's see, minus 2x minus 3 over, no, I don't want to do that actually, minus, let's do minus x minus 2 over x squared minus 4. Okay, so first you always see if you can plug in 2. And when I go to plug in 2, the top looks okay. I get 4 minus 2, which is 0. But on the bottom, I get 4 minus 4, which is 0. So a numerator being 0, not an issue. A denominator being 0, a problem. So then I see, all right, let me see if I can factor and reduce and then plug in. So the numerator factors to x minus 2, x plus 1. The denominator's a difference of squares. And There we go. Those cancel. So now let me see if I find the limit as x goes to 2. Let's see if I can now plug in. So if I plug in 2, I get 3 in the numerator and 4 in the denominator, and that's the limit. So perfect. So if you can't plug in, see if you can factor, reduce, and then plug in. A third case, say you can't do that. Well, another strategy we have is if I plug in and I get something mathematically illegal, let's see if there's a situation where I can multiply the numerator and the denominator by a conjugate. And often this is the case when you have some sort of square root. So here, notice an example in number 3. So I should have written multiply by a conjugate and then plug in. And then plug in. So let's look at the example I have here. If I plug in 0 right now, there's a problem. I can't divide by 0. So let's instead see if we can shake things up and then plug in for x, 0. So the conjugate of the numerator would be the square root of x plus 1 plus 1. And I can't just multiply the numerator by that. I've got to multiply the denominator by it as well. All right, so, and remember, the nice thing about multiplying by a conjugate, you have a difference of squares. So when I multiply the numerator, I get x plus 1, middle terms cancel, and then I get minus 1, and no need to FOIL out the denominator. Okay, so this is the limit as x goes to 0. The 1s are canceling here, so I've got x over x times this denominator. Now the x's go away, so the numerator is just 1 now. Now if I plug in 0, I can do it because I get 1 over the square root of 1 plus 1 plus 1. And let's see what that gives me. So the square root of, oh, I'm not plugging in 1, sorry. I'm plugging in 0 for x. I don't know why I was plugging in 1. Sorry. So plugging in 0 for x. So I get 1 over the square root of 0 plus 1, which is going to be 1/2. So those are the 3 strategies. Sometimes you can't do any of that. And when you plug in, you still are getting a 0 in the denominator. And in that case, it would not exist. Okay. So that is sum with limits. And the last thing we talked about is what the 1.5, which was the when a function is continuous and when it's differentiable. So that's the last piece. So differentiable. Differentiable means can take the derivative and continuous. So you can take, actually I should say it's not differentiable. So not differentiable. One, if the graph has a peak or corner, because you cannot find a tangent line at a peak or corner. A tangent line would not represent there a rate of change. And also in which direction would you put it if it's at a peak. Second, you can't find, it's not differentiable where the function is discontinuous. So if function is discontinuous at x equals a, it is not differentiable at x equals a. You can't find the equation of a tangent line if there is no point there, if there is no y value, if there's an open circle or a hole. Third case is if you had a vertical tangent line, because remember, vertical lines have no slope, so it wouldn't be differentiable there. Okay, so let's talk about continuous then. That's when you can find a derivative, or can't find a derivative rather. A function is continuous. Literally, it means it's continuous if you can draw it without ever having to pick up your pencil, meaning there are no breaks. But there is a formal definition of continuity, and that is it's continuous at x equals a if the following three things hold. First of all, it has to be defined at f of a has to exist. So it has to be defined at x equals a. Second thing that has to be the case is the limit as x goes to a of the function has to exist. So it has to have a limit. And the third case is putting these 1 and 2 together. The limit as x approaches a of the function has to actually be the y value there. It has to actually equal f of a. Okay, so that was the last piece that we talked about. And then there are some practice problems to do related to these, but that is just going through the topics that we covered.